Thank you everyone for coming. This is one of the later PhD defenses I've ever seen, 4 o'clock on a Friday afternoon. Everybody's showing up to hear science like that. It's just awesomely fantastic. You have to come to the front, Dimitri, as a recalcitrant member of the committee. So the first thing I want to do is to give a big shout out to Mia, Katie, Josh, and Ross for believing in the Robotics Institute. When they joined it, they were joining groups that were pretty well established, so there was some, cohesiveness there, but the fact that the Institute would last long enough to last to a 4th degree was far from certain. Okay? But Ross, we are still standing and very pleased to be up here and sharing this important moment with you. So Ross came to us from the University of Louisiana at Lafayette. It's ranked about the same as Oklahoma State, where I did my undergraduate, but the top students at all of these state schools are just outstanding. And I think it's really important that we search widely when we're bringing students into the Institute. Ross got off to a good solid start, but things really took off for him when Monty joined the effort and became a co-advisor. So Ryan, I really want to thank all the help that your group has provided to making this thesis possible. Because my group had worked really a long time on blind walking, and when I first talked to Ross, we were kind of floating the idea that we really needed to start bringing perception into Biped world, but I had no idea how to really do it. He had done some computer vision on like an IEEE student project, I think. Yeah, so I'm trying to pull up our conversation from 5 years ago. And I think you're all going to be impressed at what he has pulled off. So I'll give the credit, of course, to Ross, and just really want to thank Monty for joining the team as well. So with that, without further ado, all right. Ross Hartley.
Thank you everyone for coming. I'm going to talk about contact-aided state estimation on lead groups for legged robot mapping and control. So why do we care about legged robots? So first of all, wheeled robots can't access everywhere that legged robots can. You can see the vehicle getting stuck really easily on terrain that we as humans could just walk right across and it's not an issue. And furthermore, a lot of the world that we design, like our homes and our factories and stuff, these are all designed for humans and human walking. So it makes a little bit of sense to have legged robots walk similar to humans so that way we can fit these robots into these scenarios too without having to redesign factories and redesign our homes for wheeled flying robots. We also want to see if we can use these kind of robots to help replace humans in dangerous scenarios. If there's a burning building, you might not want to send a firefighter in there if you don't know that there's a human in there. So it makes sense to maybe send a legged robot to go scout out the area beforehand to kind of help reduce the risk on the firefighters' lives. And then finally, we can also use a lot of these ideas for improving prostheses and exoskeletons too. But like cars, ultimately we want legged robots to move towards autonomy. To accomplish this, I think we need robust feedback controllers, accurate state estimation, and fast motion planning. So it's really a combination of all 3 things that's going to help move legged robots towards this goal. But of course, this is really complicated for legged robots due to the unstructured nature of the environment we want them to operate in, noisy measurements coming from our sensors, switching contacts, complex dynamics, and under-actuation that's present in a lot of these systems. And of course, I don't have a solution for all of these problems, but I guess my talk today is kind of showing you the research that I've done that kind of pushes us towards this ultimate goal of bringing autonomy towards legged robots. So I'm going to talk a little bit about feedback control, but that serves primarily to motivate the bulk of my research, which was done on state estimation. And then lastly, I'll talk, I guess, next to nothing about motion planning. So first, I'll talk about designing stable walking controllers, both for Marlowe and Cassie. And then some of the work I've done on contact-aided extended Kalman filtering that helps, lets the robot estimate its velocity and local terrain information much better than we could before. And of course, this leads to some of the LiDAR mapping studies we've done on Cassie. And finally, I'll talk a little bit about how we can incorporate this kind of leg odometry into factographs for SLAM. So biped locomotion in general can be described by a hybrid system that combines continuous walking phase with the discrete impact map. The continuous dynamics can be expressed by the Euler-Lagrange equations, and then when a foot is in contact with the ground, this gives rise to an external force through a holonomic constraint that pins the foot to the ground. Impact is when the swing foot hits the ground, and typically what we'll assume is that we have an instantaneous impact map. The configuration remains constant over this impact map, but the velocity can jump so that these next domain's holonomic constraints can be satisfied. So this kind of sets up the model of legged locomotion that we're looking at. We do gait design using the hybrid zero dynamics framework, which can work even for under-actuated legged robots, where we design a set of virtual constraints that are to be imposed on the robot. So these virtual constraints look very similar to mechanical constraints, but they're actually enforced through feedback control instead of through physical connections on the robot. So here the virtual constraint is defined as the difference between an output, a desired output, and, an actual output and its desired trajectory that we will parameterize with some type of curve. So when this virtual constraint is zeroed, the chosen outputs will follow their desired trajectories as the gait progresses from beginning to end. So you can kind of see that here. So once these constraints are zeroed, the remaining uncontrollable dynamics, well, first I guess we'll do this constraint design through trajectory optimization. But then once these virtual constraints are zeroed, the remaining low-dimensional zero dynamics, so these unactuated dynamics, if those happen to be stable, then the full system can be feedback stabilizable. And the controlled dynamics, so these virtual constraint outputs, we typically can control those through a number of different controller techniques, but one that works in practice that we've been doing is just simply controlling those using PD control. So what does this trajectory optimization problem look like? Typically, we're involved in trying to minimize some costs, like energy, over one or two steps, subject to a number of constraints on the robot. So we're putting constraints on dynamics, we're putting constraints on periodicity, torque limits, joint limits, foot clearance, friction cone, all of these types of constraints that can allow the motion that comes out of the optimization to be realizable on the actual robot. We set up this problem using the fast robot optimization simulation toolbox that Younga helped build up. It takes about 1 minute to solve for a gait on Marlowe. It takes about 3 minutes to solve for a gait on Cassie. So this is pretty fast, but it's still too slow to be done online. So we can't run this optimization online and do model predictive control or anything like that. But the result of this optimization problem is a single open loop trajectory. It's only a single open loop trajectory, but we can actually run numerous optimizations in parallel if we're trying to design lots of different gaits. So for example, one thing we've done is try to generate 1,331 gaits in under 5 minutes on Cassie. But unfortunately, even perfect tracking of these outputs after we've generated them through trajectory optimization doesn't guarantee stability, since the zero dynamics may actually be unstable. So stability is often recovered through simple velocity-based foot placement strategies. So for example, the robot's being pushed forward, we'll modify the trajectory of the swing foot so that it catches the robot and keeps it upright, or through other types of adjustments. So this is typically enough to stabilize a gait such as like walking in place. So here, that's exactly what we did to stabilize walking in place right here. But a robot performing a single motion like walking in place isn't very interesting, right? What about walking forwards and walking backwards? So what you can do is go back to trajectory optimization and say, let's design gaits for walking forwards and walking backwards. So here's 11 different gaits computed for various velocities between -1 and 1 meters per second. This is the swing leg angle over the gait progression. What we can do is do linear interpolation based on the velocity to reveal a continuous set of controllers for the robot. And then from this, we can actually allow the robot to walk forwards and backwards. But why not include lateral motion too? So that's kind of exactly what we did. So we optimized a set of 121 gaits for walking forwards, backwards, sideways, diagonally, all along a 2D grid of velocities. And then we can use bilinear interpolation to choose the current gait for the robot to execute. So this works pretty well in practice. So you can see Marlowe here using this bilinear interpolation, basically choosing gaits so they can walk forwards, backwards, diagonally and sideways if we wait long enough. So I have a lot of videos, I guess, throughout this entire presentation. So this is kind of a great time to ask questions during some of these videos, I think, if anyone has any.
How do you kick it?
You can see it sideways. So I kick it right here. Yeah, so using this method, we can stabilize walking and for various perturbations, forwards, backwards, sideways walking.
So that's the one that you got a trip to Hawaii out of.
Yeah, that's right. So Dennis took this one step further. He said, well, why just include periodic gates? Why not include periodic gates and transition gates so you can transition between different speeds too? And then instead of just using bilinear interpolation, why not take all of those reference trajectories and use supervised machine learning to regress out a control policy from it? So what he did was you did this on Marlowe, and he regressed a control policy that the input to it is like measured velocity and a desired velocity, and the output is essentially the states that you're trying to track. So this worked really well on Marlowe. It allowed Marlowe to do all sorts of amazing things like walk through the valleys of the wave field. But as you can see, when Marlowe takes a step off the top of the hill, it doesn't know anything about the upcoming terrain. So the control policy gives it a desired, and the output of the control policy is a wrong desired trajectory that ultimately causes the robot to fall. So we need to know the terrain before stepping on it, so that way we can adjust the gait so that the robot can successfully walk over terrain like this. So we tried this in simulation where we went back to optimization. So we generated periodic gaits for forwards, backwards, transitions, stepping up, stepping down, and all the transitions between. And we can regress a control policy for that includes previous height and next step height. And we can actually get a controller, at least in simulation, that walks up and down these kind of hills. But Marlowe at the time didn't have any type of vision, so we could never actually try to implement this on the robot. So it was about that time that we got Cassie Blue at Michigan. So Cassie is built by Agility Robotics. It's got 20 degrees of freedom, 10 actuators, 4 springs. The default sensors on Cassie were an inertial measurement unit and joint encoders. And then we've later added onto Cassie a set of stereo cameras and LiDAR so we can start doing this perception online. So we developed a similar controller for Cassie that was based off of the Marlowe controller. So I developed a URDF for Cassie, used Frost again to generate the kinematics and dynamics model, optimized 11 different periodic gaits for walking forwards and backwards, and then the controller design used linear gait interpolation and foot placement strategy. So Yukai took these gaits, and he was able to actually implement this on Cassie to get a stable walking controller. So yeah, Yukai did the primary work of taking these gaits and actually developing a feedback controller that stabilized them on the robot. As you can see here, kind of with those range of gaits we've optimized, we can walk forwards and backwards in a similar manner. And then we took Cassie, across all sorts of different terrain to kind of test the robustness of this controller.
Is this controlled via joystick or?
Yeah, so it's basically a radio joystick that's giving commands to the desired velocity, essentially forwards, backwards, turning, sideways. And from there, based on its current velocity, it chooses a gait from that library and executes it. Any other questions about the controller?
You included sand in the optimization.
No. So yeah, that's just a testament to the robustness of the controller that Yukai designed.
Well, isn't it really 3D when he's going up and down?
Yeah, so there's small terrain heights that it's a little bit varying terrain right here, but it's not kind of these dramatic hills that we saw Marlowe stepping off of and falling. So I think Cassie can handle at least 5 to 6 centimeters up and down, maybe more. But something like 10 or 20, like 20 centimeters is around the step height of a staircase, and that's too much to remain stable on. So we've noticed a few limitations during all of these Marlowe experiments and Cassie experiments. First is we have really noisy velocity estimation. So what you see right here is what I call a kinematic-only velocity estimate. So what this does is assume that the stance foot is pinned to the ground, and it uses joint encoders and their rates to compute body velocity of the robot. And because of foot slip, because of errors in kinematics, because of noisy encoders, we get lots of noise on the resulting velocity estimate. And that velocity is, again, if you remember, used to stabilize the robot and to choose the gaits that are being executed. So it actually makes these gaits really difficult to stabilize, and it actually creates a lot of heuristic tuning problems and things like that because of this really noisy velocity estimate. And again, we have no online terrain mapping, so we can't handle really rough terrain, and we have no global pose estimate, so we can't really do any kind of global motion planning, or we can never really remove the human commands that are required for the joystick to tell the robot to go forwards and backwards. So big picture is we want both stability and autonomy. So for autonomy, this big picture is kind of inspired from human walking, I'd like to say, because for autonomy, what we really only need is a global map and pose information, but it's okay to have that low frequency. If we're trying to plan a route across town, we just need to pull out our phones, look at Google Maps, and know where we are in that Google Maps, and we can look at our phone periodically. It doesn't have to be looking at it at a high frequency for this replanning effort. Whereas if we want stability, if we want to be able to walk up into Zingerman's here, we need to know the ground slope, we need to know the step is coming up, we need to know local terrain information, we need to know our orientation and velocity as we're moving, so that way we can stabilize over this any type of terrain that's coming up. But we don't need to know where this step is, where this ramp is in a global frame. We only need it relative to where the robot currently is. So this kind of motivated a two-tier estimation approach where this global map and pose is being estimated using a factor graph-based smoothing algorithm that includes all of the measurements, including vision and LiDAR, whereas the this kind of high-frequency local odometry is being estimated using an extended Kalman filter that fuses inertial encoder and contact measurements only. And in particular, we didn't want to include vision measurements in this kind of high-frequency state estimator, because if you do something like loop closures, you get absolute position measurements, it's going to cause your position estimate to jump, and that could cause issues with your controller if you're relying on position and velocity for your actual controller. You don't want these signals to be jumping. Yeah?
With the new measuring phase difference on GPS, would you use that to get location? Would it have enough accuracy for this?
Well, I mean, if you're using GPS for position estimate, its GPS is only accurate within several meters, so that's not accurate enough to tell us where we are to get up a slope or get up a staircase or something like that. But it can certainly, I envision that helping out the problem of this kind of global position estimation. So to perform so I'll first talk about this high-frequency state estimator that we're using for feedback control. And I'm going to warn you, I have a lot of math in this section, so bear with me, but I promise I have an equal amount of videos at the end, so just look forward to that. So what we developed is a contact-aided invariant extended Kalman filter. So this estimates the robot's base pose and velocity by fusing inertial measurements, encoder measurements, and contact measurements together. This is fast converging. It can be run at high frequencies. We're running this at 2 kilohertz on the robot. And the main improvement over the state-of-the-art comes from exploiting the geometry of the problem, using Lie groups to eliminate linearization errors and reduce drift in the problem. And we developed an open source C++ library that can be used. So first, kind of a few definitions. So an inertial measurement unit provides measurements of angular velocity and linear acceleration. Inertial navigation is the process of using an IMU to estimate the position, velocity, and orientation of the robot. But simply integrating these IMU measurements is not going to give you very good accuracy of your position due to drift from sensor noise and biases. So this is the IMU we have in Cassie. It's a Vector Nav 100. It's a pretty good IMU. We consider this industrial grade IMU. But after 60 seconds, if you just integrate IMU data, you already get a 53-meter error. If you integrate for 1 hour, you're going to be off in your position by 190 kilometers. So integrating alone IMU data is not going to work. So this is what aided inertial navigation is for, which fuses inertial measurements along with some type of aiding sensor like GPS, magnetometer, landmarks, things like that to reduce or correct this drift. So on Cassie, we don't have a GPS or anything like that, but what we do have access to are joint encoders or in-contact sensors. So this motivates what I'm calling contact-aided inertial navigation, which is aided navigation using joint encoders and contact sensors. So the first assumption is we make the assumption that contact measurement implies that the stance foot remains fixed on the ground. And then forward kinematics can be used to measure this foot position relative to the IMU, and that serves as a correction. So together, if your foot's pinned to the ground and you can measure all your joint angles, that gives you a sense of what can be called leg odometry, or it gives you another sense of odometry that we can use and fuse with inertial data to help estimate the. Yeah. So one way to fuse this leg odometry with inertial data is through an extended Kalman filter, and that's been done in the past using a quaternion-based extended Kalman filter.
How realistic is the assumption that the foot will be fixed when it's not on the ground?
Right. So we're going to relax that assumption a little bit by adding Gaussian noise to it, which can allow for some levels of foot slip, but it's like, if you're walking on a treadmill or something like that where the foot is actually moving a lot, then this method won't work. So it kind of relies on that assumption, but of course, if we can be adding noise to it, we can vary the uncertainty about that noise to trust the contact assumption more or less compared to IMU and things like that. So yeah, a bit of background about Kalman filtering. So Kalman filter is the optimal linear filter if the state is assumed to be a Gaussian random variable. Of course, for most robotic systems, we don't have a linear system governing our dynamics or measurements. So this leads to the development of the extended Kalman filter, where you linearize the nonlinear state dynamics for covariance propagation for correction. But there's actually two forms of the extended Kalman filter. There's what's called the direct extended Kalman filter, which is kind of the typical one that you think of where you're filtering the states directly. And there's also what's called the indirect or error state Kalman filter, where instead of linearizing the state dynamics, you're linearizing the error dynamics instead. And the idea is that the error dynamics can be, because your error is hopefully small as this filter is running, you can, the linearity assumptions might hold better for the error dynamic as compared to the state dynamics themselves. But either way you do it, the linearization is going to depend on your current state estimate. And if you have a bad estimate, then you're going to have an incorrect linearization, and that's going to lead to poor performance. And then, of course, it cycles back, and you can, this poor performance will give you bad state estimates, which will make the linearization worse, and you could even diverge depending on how bad your estimate was. The interesting thing to note about the error state EKF is that we kind of have a choice of how we choose error in the system. If we, different choices of error variables will actually lead to different linearized error dynamics, so it'll lead to a different system. For example, using Euler angle errors versus quaternion error, it's going to give you two different linearized dynamics, and the properties of those systems will be different. So this kind of begs the question, is there a choice of error variable that leads to autonomous error dynamics? So error dynamics that are independent of the state themselves. And yes, there actually is. It's for, at least for group affine systems, and this is kind of what is working behind the invariant extended Kalman filter. So to kind of understand the workings of the filter, you kind of need to know a little bit about Lie groups. So I'm going to kind of give a very quick crash course on Lie group theory. So a Lie group is a group that's also a differentiable manifold. So examples are like a special Euclidean group or special orthogonal group. A lot of groups that we see in a lot of states in robotics are actually examples of matrix Lie groups. The Lie algebra is defined as the tangent space at the identity element of the Lie group. This vector space is isomorphic to Euclidean space Rn, and it has the same dimension as the original Lie group. So the group's exponential map will take you from the Lie algebra to the group, and the log map is the inverse that'll take you back to the Lie algebra. And the group's adjoint map can linearly exactly shift kind of a vector between two frames of reference. So we can use the adjoint, for example, to shift a measurement in the world frame to a measurement in the body frame and things like that. Or an error in the world frame to an error in the body frame. So this is kind of what it would look like for a simple circle group. But of course, for kind of an arbitrary n-dimensional matrix Lie group, you kind of have to think about it a little more abstractly. Anyone have any questions on this? So I assume we're all experts on Lie groups now. So let me move on to invariant Kalman filtering. So invariant Kalman filter is kind of this new take on Kalman filtering that can be used if your state is a matrix Lie group and your dynamics satisfy a special group affine property, which is just a property you can check on your system dynamics. For these systems, so these group affine systems, actually a very particular choice of error variables leads to linear error dynamics. So this choice is what's called the right invariant error or the left invariant error, which is just if your state X is a matrix Lie group, then it's your state estimate times your true state inverse or your true state inverse times your state estimate X. That gives you the right invariant error or the left invariant error. And it's called invariant because this error is actually invariant to the left or right actions of the group. So that's where the invariant name of the invariant Kalman filter comes from. So like I mentioned, for these systems, the nonlinear error dynamics on the group are actually exactly determined by a linear system in the Lie algebra. So all of the nonlinearities are accounted for by the exponential map. And so basically, what looks like maybe a nonlinear error system on this manifold is actually it can actually be represented by a linear system exactly in the Lie algebra. And if you're actually working with the linear system, then of course the linear assumptions about Kalman filtering hold better, so you can get better performance. Also, if your observations are of a particular form, either this so-called right invariant observation or left invariant observation, which is basically your measurement is equal to your state times a constant matrix plus noise, or your state inverse times a constant matrix plus noise, then the innovation equations also become autonomous. And this is important because if both of these kind of properties are satisfied, both the linearized dynamics and your linearized measurement models will become independent of the state estimate. So wrong state estimates won't affect the linearization anymore, and that will actually give you better performance over the standard Kalman filter or extended Kalman filter. All right. So now kind of enough background, getting back to my research. What we developed is a contact-aided invariant extended Kalman filter. So we're using IMU measurements and contact measurements for state propagation. So the IMU is used to predict the base frame movement or the IMU's frame's movement. And the contact, measuring contact essentially predicts the supporting foot movement, essentially that the foot remains fixed in the world frame. Correction is done through encoder measurements and forward kinematics to correct the state. So what does our state matrix Lie group actually look like in this case? It's this big matrix essentially where the upper left corner is the 3D orientation of the robot, and then the next column is velocity in the world frame, position in the world frame of the IMU, and then we can add on extra columns for as many contact points that we're currently in contact with on the ground. So if we have 2 feet on the ground, you'd have 2 extra columns. 10 feet on the ground, you'd have 10 extra columns, like that. So this actually forms the matrix Lie group. We call it SEK3 because essentially it's very similar to the special Euclidean group, except it has extra columns added onto it. So the input to the dynamics is going to be the accelerometer and gyroscope measurements. Like I mentioned, these IMU measurements typically have additive Gaussian noise. We'll ignore bias for now. The contact sensor indirectly measures the contact frame velocity. So when we measure we're in contact with the ground, we're inferring that the stance foot velocity is 0 plus some Gaussian noise. And then the encoders are also assumed to have additive Gaussian noise. So what does the dynamics model look like? Do we have to use this complicated Euler-Lagrange equations? And the answer is no, because we actually can replace these equations with kind of these strapped-down inertial IMU-based equations. So basically, adding an IMU to the robot or strapping down an IMU to the robot allows us to circumvent this modeling of the robot, and we can directly use the IMU measurements to propagate the state. So the first three equations here are very kind of typical for inertial navigation. It's just basically the dynamics of 3D orientation, velocity, and position. The fourth one, this D, refers to the stance foot, and essentially all it is white noise that's rotated to the world frame. So it's rotated first through the forward kinematics to get it into the body frame, and then the rotation R takes it from the body frame to the world frame. So, but ultimately it's just white noise. We can rewrite these dynamics in a matrix form, and once we do that, we can look at the deterministic dynamics, and we can see that, well, we can actually show that it does satisfy that group affine property. So again, what that means is the deterministic invariant error dynamics can actually just be described by a linear system. So when we actually do the linearization, this A matrix is what comes out. You can see the linearized error dynamics doesn't depend on the state estimate. So no matter what your state estimate is, the linearization is always the same. And of course, we could have done this for the left invariant error if we wanted to. You'll just come out with a different A matrix. It's still independent of the state, but a lot of similar properties hold. So what about our forward kinematics measurement model? So forward kinematics measures the position of the stance foot relative to the IMU. The encoder noise can be accounted for after mapping it through the analytical Jacobian of this forward kinematics function. And then once we write this forward kinematics measurement model in matrix form, you can actually see that it does have this right invariant observation structure where the measurement is equal to the state inverse times the constant matrix plus noise. So that means when we do the linearization, the linearized observation matrix also becomes state independent. In this case, it's constant. So again, no matter what our state estimate is currently, the linearized observation matrix is the same. And this ends up being the kind of the final filter equations. It's pretty much the same as a standard extended Kalman filter, where your state is propagated through the nonlinear dynamics. Your state is propagated through nonlinear dynamics, and when observations come in, your innovation is multiplied by computed Kalman gain to form a correction vector. The only difference now between this and the standard EKF is the correction vector. I mean, your state is a matrix Lie group, so you have to take the correction vector, apply the exponential map to get it to the matrix Lie group, and then do matrix multiplication to actually correct the state. But other than that, it's pretty much the same equations as the standard extended Kalman filter. So what we've done is we did an observability analysis on this filter. And in doing so, we can show that the absolute position and yaw are unobservable. So drift will occur in those states. And this makes sense intuitively, because if we take Cassie, we teleport Cassie to another location and turn it, using just kinematics and inertial measurements and contact, you can't detect that. So essentially, those states are unobservable. But the remaining states will all have local stability about any trajectory. So we tested this in simulation against the kind of a state-of-the-art quaternion-based extended Kalman filter, where we ran 100 simulations using the same measurements, noise statistics, while randomly initializing the initial orientation and velocity estimates. So the top line there is the results from the quaternion-based extended Kalman filter, where the bottom is the results from our right invariant extended Kalman filter. As you can see, even when we initialize the error plus minus 30 degrees in orientation, plus minus 1 meter per second in velocity, we get really fast convergence of our filter as compared to the other one. Yeah, oftentimes converge within like less than half a second. Another interesting thing to look at is the covariance propagation. So in this example, the robot walks forward with some initial yaw uncertainty. So as the robot walks forward, this is the plot of the true covariance. So you can see how it's kind of spreading out in these kind of banana-shaped arcs, and that's because of this initial yaw uncertainty. The right invariant EKF can actually capture that extremely well. Again, because the error in the deterministic system, the error dynamics are actually exact. Whereas if you're using the quaternion-based EKF, which typically the position is just position error is modeled just by a covariance ellipse in this kind of position space, you don't get this curved nature of the covariance. So it's not captured very well. And of course, you can take this to the extreme and say, well, what if the robot had no idea of its initial yaw angle and walked forward? And it turns out the invariant EKF can do that just fine too. We have these kind of concentric circles as the robot walks further and further out. And they're circles because the robot had no idea of its initial yaw orientation. And this is all because of this mapping from the Lie algebra to the group through the exponential map, which takes into account all of the curved nature of the space. So unfortunately, there's no known way to incorporate IMU bias in the Lie group without, while also maintaining this group affine property, unfortunately. But it turns out we can design what's been called an imperfect invariant EKF, where basically our state is now a tuple of our original matrix Lie group and the bias errors. And we'll filter the matrix Lie group similar using the invariant EKF, and we'll filter the bias states using just an typical error state EKF. And what you get is a new dynamics matrix that's kind of has this block form here. This block here is the same as the one we have originally derived. That's independent of the state, and it only depends on the state through the bias estimates. So we tested this experimentally on Cassie 2 with bias estimation enabled. So we ran the exact same experiment using same measurements. We ran the filters 100 times again, starting from different random initializations, and you can see very similar plots to the simulation results, where the right invariant EKF converges significantly faster and more uniformly than the quaternion-based extended Kalman filter.
How does the bias estimate invariant EKF compare to the non-bias estimate one? Does it make it better to start estimating bias as well?
You're asking how does the bias estimate in the non-invariant Kalman filter compare?
Or invariant Kalman filter. Like if you are estimating the bias or not, does it make it better?
So it all depends on what the bias, the true bias values are. In our case, the biases never seem to be that large, so we know it's kind of about the same. In some cases, it actually performed a little better without estimating bias. In some cases, it's but in simulation, we can set the bias levels and we can see the true convergence to those. But I'll also say that how much of the bias is observable depends on the robot's configuration, how many feet are on the ground at a given time, and other things like that. So the more feet you have on the ground, the better you are able to estimate the bias states. So I think in general, more needs to be done to look at how well it estimates bias and what configurations of the robot can put it into a better place for estimating the bias states. So looking back at our kinematic only velocity, you can see the right invariant EKF is a much cleaner signal. You get rid of most of the noise coming from the encoders only. And something I like to point out is before this blue, you couldn't even see that the robot was rocking back and forth. And now as the robot walks, this is the lateral velocity. You can really see the robot's motion back and forth as it walks. And you couldn't see that at all before. So we tested this, the accuracy using motion capture. So we went out to MAir and recorded a motion capture experiment where we started and walked kind of along a 60-second trajectory. And from here, you can really see that so there is some drift in the absolute position as kind of expected because those states are unobservable. But overall, the drift in position over 60 seconds was less than like 5% of the distance traveled. So it was pretty good odometry overall. Of course, the observable states converged very nicely to the ground truth data. for both the rotation X and Y. If you look at the kind of the rotation about the Z-axis, something interesting to note is this is the 3 sigma covariance hole. Because the yaw angle is unobservable, you actually don't even see a shrink in the covariance because you wouldn't expect it if you can't observe anything about that state. So basically, whatever the initial uncertainty about yaw was, it remained relatively constant and slightly growing due to sensor noise over that whole trajectory. But you don't really notice very much drift in the yaw angle. It was pretty accurate there. Whereas if you look at the velocity, all of the states in the body frame, the X, Y, Z are all observable, so you get good convergence for all of those states. So we tested this on a kind of a longer walking experiment to kind of test the results of the invariant EKF to see how well it does odometry. Yeah, sped up 10 times so you can see. I'll let this play through for a little while. Anyone else, any questions about?
So what if you had an optical flow sensor? Would that help you? Would that still fit into this framework? You're saying you didn't like computer vision because of absolute jumps.
Right.
Well, optical flow would avoid that.
Right, yeah. So if you're using vision to just get relative measurements like a relative pose transformation or something like that, then you may be able to fit into this framework and you won't have issues with position jumping. The problem with that is those types of measurements are relative measurements between 2 time steps. So it's really more like a process model and not a measurement model. So to be able to apply something like that, you might need to formulate it more as like a smoothing problem because basically you'll need to fuse together 2 types of propagations, the propagation from the inertial dynamics and the propagation from like visual odometry or something like that.
Another question, are we going on? I don't want to interrupt.
No, it's fine, you can ask.
I don't know if it would be applicable here, but GPS trace quaternion, they can give you a very accurate heading angle or yaw angle.
Right.
I don't know whether that would be applicable to something like this.
Right, so I think, yeah, I mean, we can definitely use additional sensors to help correct some of the drift. It's just whether or not we'd want to do that for this system because we're trying to use the state estimate here for control, so we don't want to add any kind of sensors that gives jumps in the position signals. But things like a magnetometer or GPS or something like that we can use to help correct the heading angle, which would be good. But I guess the idea is we don't, to maintain stability as the robot's walking around, we don't need to know which direction it's pointing. We just need to know where the objects in the world are relative to it. So we got a new torso and perception system on Cassie. Bruce helped a lot with getting this designed and built up. This whole perception system includes 2 extra LiDARs, 2 RealSense cameras, and then we have a NVIDIA Jetson GPU, router switch, and extra power supply in addition to the original IMU that was on there. And yeah, we faced a lot of challenges getting this working, calibration, synchronization, data collection, and some of these we're still working through today. But one of the cool things we can do with this system now that we have it up on Cassie is we can actually use the invariant EKF odometry to do kind of LiDAR mapping. So one of the things I want to point out here is we can use, because the odometry is provided at really high frequency at 2 kilohertz, we can actually use this high frequency odometry to correct Cassie's movement within single LiDAR scans. So basically taking the individual packets of the LiDAR instead of the individual point, whole point clouds and transforming them based on time steps. And what that does is, Cassie moves so much within a single scan that you can see the map kind of getting jumbled up or disconnected here. Whereas once you correct for that movement, you don't see any of those issues. And yeah, I really like this video because you can see the lots of little small details in the lab really well. You can see like the staircase, the bikes, computers, the stools. You can see Monty's hair, which is really neat. It casts a really good shadow on the wall. But you can really see as the robot's moving around, a lot of the things are staying stable and static in the world frame, which is what we'd expect if we're getting good odometry results. So you can see the bikes in the back here. So of course we took this system and we had to walk all over campus to get some really neat videos of LiDAR mapping with Cassie. And the idea here is because we're not relying on GPS or anything like that, we can go indoors, we can go outdoors. We're only using, basically it's not using the vision data at all, which you see here. It's not using the LiDAR data for state estimation. It's only using the LiDAR data, using the inertial contact and kinematics data to estimate the state, then projecting the LiDAR point clouds onto the state estimate. So this could work in the dark. You don't even need a camera, or you could work without LiDAR, I guess, too. But yeah, you can see how much the robot's moving around from the camera. This is rigidly attached to Marlow. All right, Cassie. So yeah, ultimately we want to take these LiDAR maps, build up a local elevation map around the robot, and use that elevation map or some type of map representation to help improve stability on the robot. Yeah, some of these blurs you see are just people walking by. So what we're doing here is taking 10 seconds of LiDAR data and putting it all into this common frame. So if you have dynamic objects walking around, you'll see blur from that.
Your color is depth.
Intensity, LiDAR intensity. So here's a pretty new video. We recently took Cassie out walking around kind of the plant operations building and through some mud and stuff like that. You can see, this filter doesn't make any assumptions about the terrain height or anything like that, so we can work on flat ground, rough ground, anything like that. And you can see the kind of all the ruts in the mud and stuff like that really well from the LiDAR. So something that you might wonder is, can you use invariant EKF SLAM, so adding landmarks to the state to help correct these kind of drift issues and things like that. So you can definitely do that with this state matrix. You can take the original state matrix that we had and keep adding on columns for the position of the landmarks in the world frame. And that works fine, just like augmenting state and typical EKF with landmarks. And then landmark measurements, relative measurements of the landmark relative to the robot, those are right invariant measurements. GPS measurements are left invariant measurements. Magnetometer measurements are right invariant measurements. So lots of very common robotics measurements fit all into this invariant extended Kalman filter framework. And slowly getting all these measurements integrated into the C++ library, so you can use it if you want. So this is very extendable to lots of different types of eta inertial navigation systems. Like we mentioned, inertial, kinematic, and contact only, absolute position and yaw will drift. So landmarks could eliminate drift, but of course, just like EKF SLAM, too many landmarks will make the filter intractable to run for real-time applications. So this kind of begs the question, well, can we use these ideas and extend it to contact-aided smoothing using factor graphs? So factor graphs are commonly used to fuse inertial and visual measurements together. As the camera moves around, for example, low-frequency camera keyframes can be selected. These camera keyframes become nodes in a factor graph, where the IMU and visual data provides relative measurements linking the nodes in this graph together. Then this graph can then be solved, can be optimized to solve for the robot's optimal trajectory. So solving this graph for an optimal state estimate involves solving a maximum a posteriori estimation problem, where we're trying to find the most likely trajectory that best aligns with all the measurements we've collected. Once we make independence of measurements assumptions along with Gaussian noise assumptions, this boils down to solving a nonlinear weighted least squares problem, where each of these kind of error terms account for all the different factors in your graph, like your prior, loop closure, IMU factor, visual factors, and things like that. Again, we can use Lie group theory to advance our state estimation techniques here. For example, if the the factor is Lie group based, the error residual can be defined in the tangent space. You can use Gauss-Newton on a manifold to optimize instead of just using Gauss-Newton. And of course, you can use incremental solvers to make this feasible for long-term solutions. But of course, many vision-based methods can fail. A lot of times due to scarcity of features or poor lighting. Smoke, grass, snow, things that have very few features. Sun glare, walking at night, that might be a challenge for camera-based systems. Wondering, can we enhance this visual inertial odometry methods with measurements that legged robots actually have, which again are this contact and encoder measurements. So kind of put into this factor graph framework, this is kind of what it looks like. We developed two types of factors, this forward kinematics factor that relates the base frame of the robot to the contact frame through noisy encoder measurements, and then a binary contact factor that describes how the contact frame moves over time. So, of course, between two camera keyframes, you might have multiple contact switches. So say you're sampling keyframes once per second. You could go from left stance to right stance, back to left stance within that 1 second. So this actually, to develop these factors, we actually had to use a hybrid pre-integrated contact model to account for these contact switching that can potentially happen. Once developed, now we have these new forward kinematics and contact factors. We can now solve kind of the full SLAM problem where we're minimizing the errors from the prior loop closure, IMU, visual factors, forward kinematic, and hybrid contact factors altogether. So we tested this on Cassie. We implemented these factors in GTSAM. We used GTSAM's IMU factor for inertial odometry. We used SVO for visual odometry, and ISAM2 as the incremental solver. Graph nodes were added every 3 seconds, and we used motion capture for ground truth. As you can see here, this is the plot looking at motion capture versus just visual inertial. In this case, it actually performed pretty bad because we have pretty sparse features and the camera is shaking a lot, so it was really hard to get good visual odometry there. If we use just inertial contact, we actually have better performance in visual inertial odometry for this case, and then visual inertial and contact all added together produce the best performance. So we were interested in this because this could allow SLAM systems to be more robust to perception loss. So one of the things we looked at is, well, what happens if we cut out vision data for certain segments of time? During this 10-second window and this 10-second window, we dropped out vision data. The top two plots here show the result of the nominal visual inertial trajectory and what happens if we drop vision out. So when we drop vision, we're only relying on IMU data at those times. So what this is the log determinant of the covariance. So the higher on this means the more uncertain you are. So when we lose vision data and we rely only on inertial data, our uncertainty rises because we have nothing to correct that inertial data. Whereas for the visual inertial contact plots, losing vision didn't really have a big effect on the uncertainty because we had an extra factor to rely on because when we lose vision, we still had inertial and contact data.
So you were losing vision but not putting in outlier vision data. Right,
yeah. In this case, we just dropped vision completely, essentially, as if someone turned off the lights or something when you're in a room.
What if it had an internal error and only gave you
an internal?
Like a 5% error in vision?
Yeah.
That has happened. I've seen it many times with cars.
Yeah. I think more research would have to be done to see how this kind of thing performs. But I mean, the idea is if all of your the more measurements you have, and if you're at least consistent with including those measurements into the state estimation problem, then it should only improve your state estimate ideally. So yeah, looking towards the next steps in future research. So something that we started looking into is inertial contact invariant smoothing. So it actually turns out there you can solve you can take a lot of the properties from invariant filtering and apply them to invariant smoothing. So we need to do more research into seeing how that can actually improve smoothing results. And then ultimately we want large-scale semantic SLAM for legged robots and ground surface reconstruction, so we can start using this information in the feedback controller to actually do useful tasks like, avoid the grass, stay on sidewalks, going up and down steps and things like that. Something that I think would be really interesting would be this constraints keeping the stance foot onto the reconstructed ground surface. So right now, we're just building up a map of the environment based off maybe the LiDAR data, but we have nothing physically constraining that map that we're building up to be, for the foot to lie on that map. So sometimes you might see the foot's actually a little bit below the map or a little bit above the map, but if we can actually place constraints keeping the foot onto the map, we can improve our state estimation problem and potentially improve the ground surface reconstruction problem also. And then something else that could be interesting is we're using contact measurements to infer foot velocity measurements. It would be also using different types of controller modes or trained to infer different types of measurements, like standing, inferring that the position remains unchanged, and things like that. And one of the biggest sources of drift that we've seen with either of these methods is due to kinematic errors. So if you have errors in your kinematic function, you'll see a lot of this drift. So online kinematic calibration could be useful to help improve that. Next steps towards the controller. We really want to get close the loop between perception and control. So in this video, the step up was triggered by a human pressing the button. It wasn't triggered by vision. We want it to be triggered by vision, so we can do things like stairs and slope terrain. And then ultimately, once this is all together, we want to develop a high-level planner that so that the robot can perform useful tasks without having to rely on human joystick commands. So one potential application is we could utilize the Gait libraries that we use for the controllers to do planning for the high-level planning. So that's kind of what I did there with using an RRT based on the Gait libraries. Yeah, I just want to thank everybody that's worked with me over the past number of years, and all of my committee. Really took a whole team to get any of these videos and anything working on the robot. So thank you, everyone. And questions? And I have one more video, because you can't end any legged robot presentation without some failures.
Inertial odometry failed.
Do you have a sensor for measuring the orientation of gravity vector?
Yeah, so in the accelerometer can kind of measure that, and when you combine it with the gyroscope. Yeah, we're not sure who that person is, so if anyone knows who that is, we have a good video.
Associated Press.
Ooh.
He grabbed it.
I think that was the question.
Oh, this is the one that catches fire.
I was not around.
Literally catches fire.